In this video, I will discuss the purpose of one-by-one convolutions. So basically, I will explain how one-by-one convolutions can do something useful. Say we have an input image that looks like this, and let's say it only has one channel. And say we want to apply a one-by-one filter, and let's say the filter value, since it's one-by-one, is only 0.5. So if we convolve this filter into our input image, the output, the activation is simply input divided by 2, because this 0.5 is going to multiply each input pixel in the input image, and what's going to come out is simply input by 2. So this is not meaningful at all. I mean, it's not helping learn anything new. But let's say the input actually has 3 channels, right? And then we apply the same one-by-one filter, but remember, filters have to match the number of input channels, right? So this filter actually should also have 3 values, 0.5, 0.5, and 0.5, or 0.5, something else, and something else. So this is basically a one-by-one filter, but it has 3 values in it, right? So if we convolve this filter with the input, then what's going to come out is a single channel, because there's only one filter here, a single channel output, and this activation can represent some interchannel relationship. So this single channel it can be thought of in a way as a compression of these 3 channels. Now, how it's compressed, maybe it's an algorithm, or this serves as a technique to convert color images into black and white, or do something. So here, while one-by-one convolution is not meaningful if the input is only one channel, but if the input has more than one channels, then one-by-one convolution can serve as doing something meaningful to the input image by shrinking the number of channels in the input. So it may still, your output may still lose some information, but it can do something meaningful. Now imagine having multiple one-by-one filters here, then together they could do something way more powerful. So the main purpose of using one-by-one convolutions is basically to shrink the number of input channels. For example, if we have a color image as input with 3 channels, we can apply either 3 one-by-one convolutional filters, or we can apply one-by-one convolution filter and maybe obtain something like a black and white image. So depending on the filter value. In deep learning, it's very common to apply one-by-one filters to shrink the number of input channels. So basically, this is the purpose of using one-by-one convolution. Oftentimes, applying convolutions can be very, very heavy, and there may be other advantageous things that we would like to do. Say, for example, you have an input image that's at 16 channels. Although this may sound weird, there are different kinds of images which have even hundreds of channels. These images are known as hyperspectral images. So anyway, in case of deep learning, these can be activations, but we can use, say, for example, 3 one-by-one convolutions and shrink the 16 channels into 3. And now say we are doing some heavy computation. In that case, what we can simply do is shrink the number of channels and shrink it to as many channels as we want, such that the channel save enough of resources and yet maintain the knowledge that is captured by these 16 channels. So that's the purpose of one-by-one convolutions.